Hello students, in this lecture we'll find a boundary condition of the field vectors. Now field vectors here are electric field vector and displacement field vector. So we find here boundary condition means suppose there are two dielectric. So at the boundary between these two dielectric, that means interface between the two dielectrics. Now, how this electric field vector is related and how the displacement field vector is related.
Now let's say that below this line dielectric 1 is there and above this line a dielectric 2 is there. So these are two different dielectric. So this line is the interface between dielectric 1 and dielectric 2, and the the values of electric field and displacement vectors are different in two different dielectric. So value of the electric field is E1 in this dielectric 1 and displacement vector is D1. In dielectric 2, electric field vector is E2 and displacement vector is D2. Now here the direction of E1 and E2 is different, direction of D1 and D2 is different because they are two different dielectric medium. But in same dielectric, as we have mentioned earlier, isotropic dielectric, that means all physical quantities have the same direction. So direction of vector E1 and direction of vector D1 will be same. Direction of vector E2 and direction of vector D2 is same. But in two different mediums, the vectors are have a different direction. Then to find out what are the values at the interface, that means this surface separating the dielectric 1 and dielectric 2, what happens to the electric field and what happens to the displacement vector. To find that, we take a surface which is there in both the dielectrics. So part of that surface is in the dielectric 1 and part of that is in the dielectric 2, and we take this a closed surface as a pillbox. Pillbox means just like a tablet. Height is very small as compared to area of the cross section. So this surface S we have taken and this height will be negligible and area of this delta S is delta S. Similarly, this area is delta S. Then suppose if there are charges at the interface, then the charge will be surface charge density. See, charge enclosed by this area S is this charge enclosed by this S, means inside this S will be there what is there on the surface, and it is equal to surface charge density into the area, because surface charge density is charge by area. So charge is there inside this over this surface delta S. Now let us apply the integral from the Gauss's law to the dielectric for this surface S. That means for this pillbox. So now here that displacement into the area for this is the height is negligible, we can neglect it. So now here what will happen is, where the Gauss's law is the surface integral and loop integral, because this is a closed surface, is vector d dot n cap ds, and that is equal to charge enclosed, and as we have seen in the previous slide, charge enclosed is sigma ds. Then this integral is what is there on this surface, upper surface, lower surface and this curved surface, but this height is very negligible, so the that part will be neglected. So now on this upper part, so it is vector d2, because the upper cross section lies in the dielectric 2, so it is vector d2 dot, that for this the area vector is directed perpendicular out, because direction of area vector is perpendicular out, and its unit vector is denoted as n2 cap. So d2 vector d2 dot n2 cap into area of this is delta S plus this quantity d dot nds for this lower surface, and here area of this is delta S and displacement vector is d1, and here this area vector is perpendicular out because direction of area vector is always perpendicular out of the closed surface, so it is directed this way and we are denoted as n1 cap, and that is equal to sigma ds. Then ds cancels throughout and we get this equation. Then we find here that since for upper surface and lower surface these area vectors are perpendicular out, so they are in opposite direction. Since these are in opposite direction, the magnitude of this unit vector is 1, opposite direction. So n1 is minus n2. Then the dot product d2 dot n2 cap. So magnitude of this d2, magnitude of n2 cap is 1, cos of theta 2. Theta 2 is the angle between d2 and n2. So this d2 and n2, this is that angle theta 2. Then minus magnitude of this is d1, magnitude of n2 cap is 1, and cos of theta 1 is angle between d1 and n2. So d1 is, if you draw it like this, then angle made by this d1 with this n2, that is theta 1. Now these are called as a normal component because they are in the perpendicular direction. So these are the component of d2 in this normal direction. They are called as a normal component. Then we write this d2 cos theta 2 as d suffix 2n. That means this is a displacement vector in the magnitude of displacement vector in the dielectric 2, but in the normal direction because d2 cos theta 2. Similarly, d1 cos theta 1 is written as d suffix 1n. So this magnitude of displacement vector in the dielectric 1, but in the normal direction. This is what we found in the previous slide. Suppose there are no charges at the interface. So here at interface there are no free charges. So rho is 0. Surface charge density is 0. So if this is 0, then d2n equal to d1n. But as we have written earlier, d2n is the normal component of d2, which is d2 cos theta, and d1n is the normal component of d1, which is d1 cos theta 1. So this normal component of the displacement vector are continuous. So they have the same value, only one value at the interface. That is what the meaning of the continuous. Then to find out what is the relation between E1 and E2 at the interface, what we consider here is a closed path like this, A, B, C, D, A. Now here we neglect this BC and AD, will neglect, and here this since it is a closed path, this electric field into the length, the total will be equal to 0. So here it is vector E2 dot delta vector L. So this is the delta L, this length AB is delta L. So E2 dot delta L plus E1 here, and now here what happened is this length and this length is same, but direction of this is opposite. So it is E1 dot minus delta L, and that is equal to 0, and this becomes this one, vector E2 dot delta vector L minus E1 dot delta vector L. Then angle between E2 and delta L. See this angle between, see this D2 is parallel to E2 because for isotropic dielectric the direction of all physical quantities have the same direction. So these are this. So if this D2 makes angle theta 2 with N2, that means E2 will also make angle theta 2 with N2. That means it will make angle 90 minus theta 2 in the direction of delta L, that is AB. So this is theta 2. So this will be 90 minus theta 2. So that's why when you take a dot product, angle between E2 and delta L, so E2 and delta L is 90 minus theta 2 because theta 2 is angle made by E2 with the normal. So angle made by E2 with this horizontal direction is 90 minus theta 2. So we are written E2 delta L cos 90 minus theta 2 minus here when you take a dot product E1 delta L. and angle between E1 and delta L. See, this E1 and this delta L. Now here the angle again similar to this, it is theta 90 minus theta 1. So this is equal to 0. Then delta L cancels and cos of 90 minus theta 2 is sin theta 2. Cos of 90 minus theta 1 is sin theta 1. So what you get is E2 sin theta 2 minus E1 sin theta 1 equal to 0. So E2 sin theta 2 equal to E1 sin theta 1. Now this E2 sin theta 2. So E2, so its component, see if this angle theta, this component will be E2 cos theta 2. So this will be E2 sin theta 2. So this is the component in the direction of AB, that is called as the tangential component to this AB. So it is written as E2 sin theta 2 is written as E2t, t means a tangential. Similarly, E1 sin theta 1. So it is a tangential component of E1, and here they are equal. So hence the tangential component of electric field are continuous at the interface.